This is logic and computer design fundamentals, and we will check chapter 3, the combinational logic design. We will specifically talk about the implementation technology and logic design. As an overview, we will check the implementation technology and logic design. We will go through the design concepts, the design procedure, including specification, formulation, optimization, technology mapping, and verification. In the technology mapping, we will see how to do this mapping from and, or, and not, and also the gates, and also other type of gates. So we will talk about the verification, and its main job is answering this question: does the design circuit meets the specifications? The combinational circuit. Actually, a combinational logic circuit has a set of M Boolean input, a set of N Boolean output. This is N Boolean output, and N switching functions, each mapping the 2 to the power M input combination to the output, such that the current output depends only on the current input value, meaning this output, which is one of the N Boolean outputs, it's a function of all the M Boolean inputs or some of them. The hierarchical design to control the complexity of the function mapping inputs to the outputs, we need to figure out a way to make it easier for the logic designer. So we decompose the function into smaller pieces called blocks, and then we decompose each block's function into smaller blocks, and we keep repeating this process as necessary until all blocks are small enough to be managed by one developer. Any block that is not decomposed is called a primitive block. The collection of all the blocks, including the decomposed ones, is collectively called a hierarchy. As an example, if we say that we have 9 input parity tree, we will check this in the next slide. The top level, we will see that it has 9 input and 1 output. And then we will try to break it down in the second level, the third level, up to the primitives. And we will find out at the end that we need 32 2-input NAND gates. And to check this, you can see here, that's a parity tree example. It has 9 input starting from x0 to x8, and it's generating one output, Z0. The circuit, now we break it down into 4 blocks. Each one of them is having 3 inputs and generating 1 output. Similarly for this one and for this one. Since those generate 3 outputs, we can input them into this 3-input even function to generate the final output. Each one of these 4 blocks is actually a 3-input XOR gate that is designed by 2-input XOR gates. And there are 2 versions of them. Each XOR in turn is designed using NANDs, using only NANDs. So if you want to try to find how many NANDs in the full design, each XOR now having 4 NANDs, and this one also have 4 NANDs. So the total is 8 NANDs. We have 8 here, 8 here, 8 here, and 8 NANDs here. So for the full design, we will need 32 NANDs. And this confirms what we say here. Now the second level has 4 3-bit parity trees. The third level has 2-bit, 2 of the 2-bit exclusive OR functions, and the primitive have 4 2-input NAND gates. And the total will be 32. So this is how we did the abstraction, and we make it easier to understand. The reusable function, whenever possible, we try to decompose a complex design into common reusable function block. These blocks are verified and well documented and placed or in an organized way in libraries for future use. So if you have a new design, you just pull what you need from the already made library. Let's see this example, which is a 4-bit equality comparator. So we have two numbers, A and B, A being A0, A1, A2, and A3, and B being B0, B1, B2, and B3. We want to check if they are equal to each other. So we have this block called MX. We will give A0 and B0 for checkup if they are equal or not, and we will generate N0. Similarly for A1, B1, A2, B2, and A3, B3. The resulting N's, starting from N0 to N3, will go to this block, which we call ME, to get the final result. Now, each one of these N follow this function, which is basically an XOR. It's an XOR. You know, it's AI bar BI or AI BI bar, meaning this MX, this block, inside it, we have an XOR gate that is implemented using AND and OR. Two level, you have AND OR with the inverters. And that's the other way of implementing an XOR gate. So basically, this equality comparator checks if any difference between the bits between the bits starting from A0 to A3, B0 to B3. If there is any difference, the MX block will give 1. If all of them are equal, each one of them will give 0. Now, these outputs, the N's, will be the input for the ME block, and the ME block is a symbol for input NOR gate. And if you have zeros, which means A and B are equal, it will generate 1, meaning that they are equal. Other than that, if there is any one here, which includes all the other 15 cases, will give E equal to 0. Now, the hierarchical design for the 4-bit equality comparator will have 4 XORs, which we called MX, and each one of them inside it, we have a single OR, 2 ANDs, and 2 inverters. As you can see it here, single OR, 2 ANDs, and 2 inverters. The ME have only a 4-input NOR gate. And we can say the same thing in a short way, this way in the figure B. The 4-input equality comparator will have MX that has AND, OR, and an inverter, and ME block that has only an OR gate. So from what we've introduced so far, we have 2 ways actually to design any logic circuit. We have a top-down design or a top-down approach that proceeds from an abstract high-level specification to a more and more detailed design by decomposition and successive refinement. While the other way around, we have a bottom-up design that starts with detailed primitive blocks and combines them into larger and more complex functional blocks. The designs usually proceed from both directions simultaneously. The top-down design answers what are we building, and the bottom-up design answers how do we build it. The top-down controls complexity, while the bottom-up focuses on the details. Now, the integrated circuit, informally saying, called chips, or a single chip, is a semiconductor crystal, often using silicon, containing an electronic components for the digital gates and storage element, which are interconnected on the chip. The main element that we are using in chips are the transistors. And they have 2 types, the NMOS transistor and the PMOS transistor, but this is outside of the scope of this talk. We have some terminologies that specify the levels of chip integration: SSI, MSI, LSI, and VLSI. There are also more modern ones, but those 4 would be enough for now. SSI is a small-scale integrated chips. MSI is medium-scale integration. LSI is large-scale integration, and the VLSI is a very large-scale integration. And you can see that the SSI has fewer than 10 gates, the MSI between 10 and 100, the LSI from 100 to 1,000 of gates, and the VLSI from thousands of gates to 100 of millions of gates. Now, there are many terminologies that we use to describe the properties of a gate. Those are the technology parameters, which is a specific gate implementation technology, are characterized by the following parameters. These are the parameters: the fan-in, which is controlling the number of the inputs available on a gate; the fan-out, which tells you the number of the standard loads driven by a gate output. So it's basically tells you how many connections that you can give a certain output to a successive gate. the logic levels, this signal value that ranges from 0 and 1 on the input. And basically, we have certain logic levels. At the end of the day, we want two values, logic 0 and logic 1. The noise margin, which is the maximum external noise voltage, that is superimposed on a normal input value, and which will not cause an undesirable change in the circuit output. So the noise margin is actually giving you a limit that you can tolerate, and you still can distinguish between the logic 0 and logic 1. The cost for a gate is a metric or a measurement of the contribution by the gate to the cost of the integrated circuit. The cost could be, we could refer this to area, power consumption, delay. There are many types of costs, or we can make a combination of these measurements. The propagation delay is the time required for a change in the value of a signal to propagate from the input until you get the output. So there is a certain delay through the gate, and we will call this propagation delay. The power dissipation is the amount of power drawn from the power supply and consumed by the running gate. The propagation delay is the time for a change on an input of a gate to propagate up until you reach the output. This delay is usually measured at the 50% point with respect to the high and low output voltage level. And we will see this clearly in the next figure. The high to low, we will distinguish between the high to low and the low to high. So we have a certain time, TPHL, and another time which is called TPLH. Those two time changes, or the changes that happens in those two times, may have different, may contribute to having two different propagation delays. And to find a unified propagation delay for a certain gate, you might use the maximum or the average of those delays. You have the high to low and low to high transition that are defined with respect to the output. A high to low input transition causes a low to high output transition if the gate having an inverter, or it will keep it the same, high to low output transition if there is no inverter. To see this details, you can see it here in this figure. This is the input and the output. Let's suppose that the input was logic 0, and then it was going up to logic 1, and then go back again to logic 0. It cannot, the input cannot suddenly move from 0 to 1 at a very high speed, or this way. This is actually the ideal case, but it never happens in real life, because when you change the input from 0 to 1, it takes some time to start accumulating the current or the voltage needed to have a logic value, whether it's low or high. So if you transition from low to high, you will take some time. If you transition from high to low, you will take also some time. This behavior happens also in the output. In addition, you will have certain delay between the input and the output. So this delay is called TPHL, which is the time or the propagation time from high to low. Notice that we define this time with respect to the output. And we have another time, which is from low to high. Now, if you want to find the propagation delay for this circuit, which is a simple inverter, then you will get the maximum of those two times. If you take the maximum, this means that you are considering the worst case scenario, which is a good idea in logic design. Propagation delay, the delay measures are measured at the midpoint between the low and the high value. As you can see, we measure it here at the 50%, also here at the 50%, and we check it also in the output. And after we have these or draw these dotted lines, we can know exactly what is this time and also this one. We have many delay models. One of the simplest delay models is it has transport delay and inertial delay. The transport delay is which is a change in the output in response to a change in the input. So this change will occur after a fixed specified delay, and we will call this delay a transport delay. The inertial delay is similar to the transport delay, except that if the input changes such that the output is to change twice, meaning you have movement from low to high or high to low in a time interval less than a period of time, a specific period of time that we call rejection time, then the output changes does not or do not occur. None of the changes we will consider if it doesn't satisfy the rejection time window. The model's typical, the inertial delay models typical electronic circuit behaviors, namely reject narrow pulses like glitches or high pulses that have a very small period of time. It helps in rejection these noises. To see an example, let's say that you are trying to get A and do it B. This is A and this is B. We randomly have these values for A and B, and we are trying to get the output. Now, if you don't consider delay at all, if you have 0 and 0, then the AND is going to be 0. Actually, the AND is always 0, except when you have A and B. Both of them are 1. So here you have both of them are 1, so it's 1 here. It will keep having 1 in the output until one of them goes to 0. It will go to 0 and keep at 0 since one of these inputs are 0 until both of them become high. You can see that there is the intersection between them here. We have A is 1 and B is 1, so you will have it as 1. And then it will go to 0 because B is going to 0. And after that, it will keep at 0 because now A is 0. And you have a small pulse here because both of them are 1. It will go back again to 0 because you have this low value of P. And after that, both of them are high until the end of the timing diagram. And the output will be high. We didn't consider any type of delay, no delay. Now, if you consider the transport delay only, so you will have certain transport delay. This transport delay, let's assume it's 2 nanosecond. So this 2 nanosecond is pushing the this curve to this direction for 2 nanosecond. You can see that it's the amount of time from here to here is about 2 nanosecond, which is the blue line that you can see over here. If we say that we are defining a rejection window time, which is 1 nanosecond, and it's the black line here, then the inertial delay will consider the change in the output only if you satisfy this window. So you can see this will be okay. The change here will be okay. The change here will be okay. But this one, since it's a small pulse, and this small pulse is less than this window, it doesn't appear in the output. To make sure that you consider all the changes, whenever you have a change, you will draw both timings, the propagation delay in blue, and you will have this rejection time. Similarly here, there is a change, so we draw it. Another change, we draw this. And here, here, and here. And you can see, since this change is less than the black line, we don't consider the change in the output. We also don't consider this, even though it's on the margin of the window. And we also don't consider this change. So you will have this high time, and you will keep at 0 until you go back to 1. The fan out can be defined in terms of a standard load. So one simple way to do it, if one standard load, we will assume that one standard load equals to the load contributed by the input of one inverter. The transition time, which is the time required for the gate output to change from high to low, we will call it THL, and from L to H, we will call it TLH. Now, the maximum fan out that can be driven by a gate is the number of standard loads the gate can drive without exceeding its specified maximum transition time. The fan out loading a gate output affects the gate's propagation speed. And to give you an example to understand this, let's see this one. The propagation delay, TBD, is affected by the following. You will see that there is an inherited gate delay, gate D, and we have a number of standard load driven by the output, which is SL, standard load, and we have the delay per standard load, which is SLD for delay. The simplest formula that we can use to calculate the propagation delay is this inherent delay, gate delay, plus the standard load delay times each standard load. And to explain this to you, assume we have this gate, and we want to find the propagation delay for this 4-input NAND. Now we know that the inherent gate delay, gate D, is equal to 0.07 nanosecond. And the SLD, which is the standard load delay for the 4-input NAND, is 0.021 nanosecond. And it's connected to 3 different gates. The standard load here is 0.8, the standard load here is 1, and the standard load here is also 1. So for a 4-input NAND gate, which is this one, you will have the propagation delay as 0.07, which is the inherent gate delay, plus the SLD, which is 0.021, times those, or the summation of those standard loads, 0.8 plus 1 plus 1. And the resulting propagation delay is 0.129 nanosecond, meaning that you will spend this amount of time going through this 4-input NAND if it is driving those 3 circuits. The circuit delay model. Now, since we know how to find the propagation delay for any circuit, we can, if you assume this simple circuit that choose between A and B. So you have S that selects the output will either have the value of A or the value of B. Now, since we already know a way to figure out what's the propagation delay for this circuit, now we can write this number, which is 0.129 nanosecond over here. And we say that this is the propagation delay for this circuit. Now, we did the same for all these circuits, and we write the propagation delay inside each gate, 0.2 for the inverter, 0.4 for the AND, and 0.5 for the OR. Now, to find the full circuit propagation delay, we calculate the propagation delay for each gate, as we explained earlier, and then we find the critical path, because it is like different roads that you can propagate through until you reach the output. So you can, a signal can go through this line until it reaches the output. It can also go through this line until it reaches the output, or this one, or this one. So you can see that there are 4 different paths. You should find the critical path first, which is, you can see that the longest, the path that will have the longest time would be this one. So we call this a critical path, and we name it by S inverter, and OR. S inverter and OR, and then you reach to the output. This is your critical path, and the circuit now propagation time is 0.2 plus 0.4 plus 0.5. And this will give you the 1.1 nanosecond propagation delay for this circuit. So it's very important when you try to find the circuit delay is first identifying the critical path and then find the propagation delay. Now, after we accumulated enough knowledge throughout the series of the videos that we had previously, now we can define the design procedure. It starts with the specification, which is actually a written statements. You can write a specification for the circuit. If one is not already available to you, you can write it in simple English. And then you do formulation. And the formulation has many methods. You can drive a truth table or the initial Boolean equation that defines the required relationship between the input or the output, or you can even have the Carnot map for it. After you do the formulation, you would do the optimization. The optimization, we apply the 2-level and multiple level optimization that we studied to finally generate or draw the logic diagram or provide the netlist for the resulting circuit using ANDs, ORs, and inverters. And remember, we have standard forms like the POM or the SOM. The technology mapping maps the logic diagram or the resulting netlist to the implementation technology that was selected. And the verification, when you're done with your design, you verify the correctness of this final design. Well, the specification is simple English statements, and we had many questions in English, and based on them, we formulate the truth table, the Boolean algebra, and we end up with doing the optimization and draw the logic diagram in a previous classes. The technology mapping, it has certain chip design styles. It has cells and cell libraries, and you could do the mapping of techniques. The mapping techniques, maybe you want to design the whole design only using NAND gates or using NOR gates or using certain number of NAND gates with certain other certain numbers of NOR gates, uh, and or multiple gate types. For example, if you have a design and you want only to design it using AND or XOR and probably inverter, you can have these conditions and you do the mapping based on these assumptions. The chip design styles, it could be full custom or standard cells or gate every. The full custom design, it has the entire design of the chip down to the smallest detail of the layout performed completely. This is why it's expensive, and it's only justifiable to be used only for dense, fast chip with high sales volume. Or you could use a standard cell, which are blocks that has been designed ahead of time, or as a part of previous designs. It has an intermediate cost. It has less density and speed compared to the full custom. The gate array is a regular patterns of gate or transistor that can be used in many designs easily. It only have the interconnection between gates that should be specified during the design stage. It has the lowest cost and the less density compared to full custom and standard cell. I like to give the example of cars and regarding the design styles. Sometimes you want a fully customized car, and this would be very expensive because you will add certain things that are not usually in the standard design, which is the standard cell. The gate array is like the primitive car that has only motor, wheels, and one seat, and that's it. And you can figure out the functionality easily by changing only few things in the car. That is, if you want to compare it to the chip design styles. We will have some examples. So if you have standard cell library, it will be something like this. This is a library. You have cell names. You will have a certain inverter that has this symbol. It has certain area, which is 1. This is the normalized area. It has a typical input load, and it has certain delay or standard load. You have 2 input NANDs like this one. You have 2 input NOR like this one. And you also have this circuit, which is the 2 ANDs followed by a NOR gate. If you go to templates, you wanted an inverter, and you find an inverter as you need it. And so you can grab the inverter and use it right away. You go and check for NAND and you found it. You try to find NOR and you couldn't, but you could build the 2 input NOR using the inverter and NAND like this. Similarly, for this design, you could build it like this. So we should discuss mapping any design to NAND gates, and similarly, how to map any design to NOR gates. Because sometimes in the libraries, you have only NANDs or only NORs. So here are some assumptions. The assumption that the gate loading and delays are ignored. The cell library contains an inverter and an in-input NAND gates, whether it's 2 input, 3 input, 4 input, and so on. And an OR, the and the OR gate and the inverter gate schematic for the circuits are available. The mapping is accomplished by replacing the AND and OR samples and pushing the inverters through the circuit fan-out points and canceling inverter pairs along the way. So you do it this way. The NAND mapping algorithm, you replace any and OR this way. The AND will be replaced by a NAND followed by inverter, followed by an inverter. And you can see that you can check if you take this bubble and you cancel it with the inverter, you go back to the AND gate. So now the AND is easy. When you want to map to NAND, the AND is fairly easy. You just put bubble, and after that, you had an inverter, so you don't change the functionality. The OR, any OR, you change it to NAND this way. So you convert the OR to AND, and then you invert everything. You invert the output and every input. This way, you will convert the OR to NAND, and those bubbles in the input will be inverters. You repeat the following pair of actions until there is at most one inverter between the lines. So if you have two inverters this way, it will be a solid line. They will cancel each other. If you have an inverter and after that you have branching, this inverter will be transferred to every branch. You can take it out from here and you put it in every branch. This is what we mean by that if a circuit input or driving NAND gate output and also the attached NAND gate input. Here's an example. If you have this gate and you work on it, you started from, let's say, specifics, certain specification, you came up with the Carnot map, you optimize it, and you came up with this design at the end. How can you transfer this design to only NANDs and inverters? To do this, you could do it by taking any NAND and replacing it with a NAND followed by inverter, NAND followed by inverter, a NAND followed by inverter. The OR, you take it out and you replace it by group of inverters followed by a NAND, as we agreed on in the previous slide. Now, after that, you keep those two inverters the same. After that, you try to simplify by taking out some of the inverters. You can see that this inverter, you can take it out, the inverter number 5, and you put it in both branches here. So you put it here and also here. The 5 will cancel the 6, and this 5 will cancel the 7. So this inverter actually is canceling the 7 and the 6. Inverter number 1 is also canceling inverter number 2. Inverter number 3 is canceling inverter number 4. And the rest will be the ending resulting or the end result circuit. So you'll have this NAND, you'll have also this NAND, and you'll have this NAND at the end, and you'll have the inverters 8 and 9 here. We could do similar thing for mapping to NOR gates. So again, the assumptions, the gate loading and delay will be ignored. The cell libraries now, you have as many number of input as you need of the NOR gates, and the AND or inverter schematic for the circuit is available. The mapping is accomplished by replacing the AND and the OR samples and pushing the inverter through the circuit up to the output. And if you have certain inverters, you could cancel them together. Now, the NOR mapping algorithm, to convert an OR gate to NOR, it's fairly easy. You just put a bubble with an inverter. For the AND, you will do it this way. you will convert the and to or, and then you will put a bubble in the output and in every input. This or with the inverter at the output is a NOR gate, and those bubbles will be inverters. And the same thing for the inverter that we discussed in the NAND mapping. Now, if you have the same example and now we want to transform it to NOR, so the AND will, every AND will be represented by a NOR with inverters, NOR with inverters, NOR with inverters. And this OR is simply represented by a NOR followed by an inverter. After that, you can see that you could cancel the one, inverter number 1, with 2 and 3. And you will end up with all this resulting circuit if you also cancel those 2 inverters in this line. So you will have 3 inverters, those 3 inverters, and you will have 4 NOR gates. This is 4 NOR gates, and this inverter at the end. If you compare both designs here, let's count the number of gates only. We have 1, 2, 3, 4, 5, 6, 7, 8 gates. We have 8 gates here. And those 8 gates are 4 NOR gates. One of these NOR gates is 4 inputs, and the rest are 2 inputs. And you have 4 nuts, or 4 inverters. If you go back to the NAND, we have 1, 2, 3, 4, 5, 6 gates. So you can see that for this circuit, mapping to NAND is better. It has 4 NANDs, and one of the NANDs is 4 input, and it has only 2 inverters. As a design example, let's say you want to, this is the specification, you want to design a BCD to X3 code converter. So you go back to what we studied, and you know that the BCD is starting from 0 to 9, this way, and the X3 for 0 is this way, and for 1 is this way. And if you remember, we divided the truth table into 2, and one of the properties of X3 is that the 0 is the opposite of the 9, and so on. So this is the X3, and you want to design a BCD to X3 code converter. The X3 code words for digit 0 to 9, adds 3 to each BCD code word. So if you have a 0, you will add 3. This is 3. 1 plus 3 is 4. 2 plus 3 is 5, and so on. 3 plus 3 is 6, and 4 plus 3 is 7. Now, if you want to continue up to 9, 9 plus 3 is 12. So the implementation, you could use multiple level circuit with NAND gates, including inverters. The formulation, you convert the 4-bit codes. You make a conversion of 4-bit codes that can be most easily be formulated by the truth table this way. So that's your first formulation. You constructed the truth table, and you know that the other codes after the 9, which is A, B, C, D, E, and F, or 10, 11, 12, 13, 14, and 15, we will consider them as don't care when we do the optimization. Now, after that, you will go to the optimization stage, and you could say that I have 4 outputs, W, X, Y, and Z, and for each one of these outputs, we will have its own K map, W, X, Y, and Z. For example, if we consider the W, you will go back to the truth table, and you will find that the W is 0, 0, 0, 0, and then 0, 1, 1, 1, So it's 0, 0, 0, 0. I mean 0, 0, and then 0, 0, 0, 1, 1, 1. And the last two rows is 1, 1. And the rest are don't care. You can do the optimization this way. We circle those 8 together, those 4 together, and those 4 together. Always don't forget to worry about the edges. There are no edges here, but for the other ones, you have edges, as for example, this one. Also, these ones, we have edges here. So this one would be A, to represent A. This square represents B, D, and this square represents BC. So this is the function of the W. Similarly, we'll find the function X, Y, and Z. After that, for these functions, we copied them here again, and we tried to do more optimization by applying certain transformations. You can see here that a quick look here and try to find what's the cost. The cost is the number of laterals, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So you have 16. Notice that we didn't consider this one because it has a function that has only one single variable. So you have 16 plus you have 7 terms, 1, 2, 3, 4, 5, 6, 7 terms, plus we consider only G, so we don't care about the inversion. So it has 23. We excluded this one, as you can see. We can reduce the number. Notice that we already made the optimization. So we believe that this is the simplest possible function of each one of the output, W, X, Y, and Z. But we did more optimization to try to reduce the cost even further. What we did here, we perform extraction by finding the factors. So we did it this way. We find out that we could define T1 as C or D, because you notice that there is C and D here, and the B could be taken as a common factor. Also, there is C and D here, and you could take it as a common factor. So you injected the T, you define T1, and you replace it here and also here. And by doing this, you reduce the cost from 23 to 19. And we will check the number 19 in the next slide, as you can, we'll see it soon. You could also reduce it by doing an extraction using Boolean transformation, because we know that the C bar, D bar is equal to, from De Morgan law, the C or D all bar, which is actually the C or D that we already defined, T1 bar. By doing this, you could now also have T1 here and also here, because you notice that you have C bar added with D bar, and you also have it here. So you take it out and you replace it by those values. All of these transformation in hope that we are reducing the cost of the function, and we really reduce it to 16. The next slide, we took this one. We're trying to design this one. So this is T1, C or D, and you can see it here, C or D. W is A or B added with T1. So it's A with B added with T1, and that would be the W. The X will be B bar T1. So you take B bar with T1, and you will have the other term B, C bar, ANDed with D bar, B, this is B, and you have C bar, ANDed with D bar. We took D bar from here. And you can do it also for Y and Z in the bottom. And you can see that those blue dots correspond to the input of each gate here. And the last level, it has the terms, which you can see it in the red square. If you count these dots, there will be 19, as we found out that the cost is 19. So now you can transform this design that you choose using a certain standard cell, and probably you use the same table that we had before, this table. If you adopt this table, then you can use these cells, and you can use these cells here in that circuit, and you transform it this way. You can notice that the OR, we replace it by NAND. The ANDs, some of the ANDs here, we replace it to NANDs. This one has been replaced in another circuit, and so on. So you can have the function, and this also tells us that you can draw the block diagram for the function, for a certain function in so many different ways.